Hi, my name is Rebecca, and I'm a fourth-year EECS major.
Hi, I'm Evan. I'm a fourth-year eecs major. Our project will be a literature review on sampling-based planning for non-holonomic systems with obstacles. I'll quickly break down the problem statement. Motion planning for non-holonomic systems with obstacles refers to the generation of open-loop control inputs to accomplish some state space goal. We assume that we have perfect knowledge of the obstacles, constraints, and dynamics of the system. By efficient, we mean that we want to be able to plan in real time. This is a fairly heuristic specification, but basically we want to be able to generate plans for Baxter as fast as MoveIt does, or fast enough that a self-driving vehicle could plan to solve a lane-changing task in real time. By near optimal, we mean that we want generated plans to be smooth and require a minimal amount of input force. Overall, this is a hard problem to solve because it is very general. There are no guarantees about the obstacles or environment. We will be coming up with our own algorithm that synthesizes some previous approaches in order to solve a toy problem that is difficult enough to be interesting. We care about solving this problem because a good solution would have positive implications for any non-holonomic system with obstacles. These include cars, UAVs, and possibly even Baxter. In terms of previous solutions to non-holonomic motion planning, we have seen several in Project 2 of this course. Optimization-based planning will generally return excellent solutions, especially when the criteria for a solution's quality are part of the constraints or optimization objective. However, optimization often takes a very long time to run, and it can be difficult to adapt to new situations such as differently shaped constraints. We put steering with sinusoids down on the slide because it was an example we covered in class. But we're really talking about the general class of solutions that use mathy control theory. It's possible that such methods might eventually end up being good solutions to this problem, but for now they have a hard time with obstacles and making trajectories optimal. As we saw, there were many not very smooth paths generated. The last class of solutions we have listed here is planners that use some kind of randomness, sampling-based planners. These include several variants of RRT that have been adapted to non-holonomic systems. These methods tend to fit our criteria for efficiency and handle obstacles very well. However, adaptations like the RRT with motion primitives used in Project 2 tend to give trajectories that aren't very smooth. We aim to add to the body of work that has been done on RRT for non-holonomic systems and hopefully achieve smooth trajectory generation without sacrificing efficiency or adaptability to obstacles.
So far, we have been reviewing existing literature, especially various flavors of RRT star, which vary in their sampling heuristics and path construction. Two grid-based approaches have stood out to us. The first involves discretizing the state space, pre-computing optimal motion primitives to all the discrete points within a neighborhood of a start point, and running RRT star using these primitives while sampling from the discretized space. The second involves hierarchically constructing increasingly expressive motion primitives from a finite set of basic motion primitives. This work was inspired by thinking about a multi-agent setting, where computing a centralized control policy built up of simple primitives becomes exceedingly computationally expensive with the added agents. To manage this complexity, the researchers designed a way to build up motion primitives, allowing more abstract motions to be constructed. Rather than using simulation software, we plan to work with the code base provided in Project 2. We're interested in using techniques we've read about to build a diverse set of motion primitives in a continuous space. We want to use hierarchy to learn about the best ways to establish a suitable abstraction level at which to make planning decisions. Considering the problem of autonomous driving, for instance, high-level decisions are generally made to establish a route. Then localized planning decisions have to be made to plan for things like lane changes, road topology, etc. Moving forward, we want to start implementing techniques we've learned about to experiment further, and we also want to do more research to learn about work that has been done in selecting these abstraction barriers.
Our hope is that a diverse enough set of motion primitives constructed hierarchically will be a good solution to our problem. The main support we have for this hypothesis is that our technique is an approximation of how humans do motion planning. In the case of walking, our brains have learned one or more compositions of muscle movements that correspond to taking steps and turning in various directions. The actions of stepping and turning can certainly be thought of as actions on a higher level of hierarchy than the action of lifting one's leg or the individual impulses sent to our muscles. Our hope is that our approach mimics the structure of human cognition enough to generalize well to different environments than the one we will be working with. One advantage that the human brain has is a period of learning, i.e., infants spend around a year learning how to walk. We might try to incorporate some kind of pre-processing for learning motion primitives to address this difference. These are some of the papers we collected as part of our literature review effort. The last two on this slide are particularly relevant to our planned approach to the problem, while the rest are more general background on RRTs and sampling-based planning. Specifically, we will likely follow the approach of sampling-based optimal kinodynamic planning with motion primitives paper, because we are essentially solving a similar problem with a different technique for generating good motion primitives. The hierarchically consistent motion primitives for quadrotor coordination paper contains some work on generating hierarchical motion primitives we will likely base our work on as well.